Today we're going to be talking about enhancing LLMs with stage grouping and dehallucination for header file decomposition. So this is the outline we have for today, and let's go right ahead and jump into the problem. What is a God header file? So if you compare it with a normal header file is small, modular, and specific to a single module, whereas a God header file contains hundreds of loosely related declarations accumulated over time as projects grow, and then they also affect many source files, as you can see on this graph as an example. So high coupling is when modules or classes are heavily dependent on each other, and then the concept of a God header file is very similar to a God class, if you will. So off the back, you think, why aren't LLMs solving this issue already? But in reality, there is a promise versus a reality to the LLM. So the LLM promise that they understand semantics, that they learn from billions of lines of codes, but in reality, there's that limited context window for the semantics for the LLM. And in terms of learning billions of lines of code, their LLMs hallucinate. And hallucination is when an AI model generates false and fabricated information while presenting it as a fact. But this happens because models are based on training patterns and not true understanding. So going back to the promises, right? A LLM can promise that you can infer developer intent, but in reality, they make up entities. And then they also promise that flexible reasoning, but in reality, they're unreliable for specific tasks. So LLMs are primarily driven by syntax, but offer little semantic understanding based on your training. And the traditional metrics versus LLMs have their pros and cons, but we need to figure out a way to combine them both. So that raises the question, how can we combine the precision of static analysis with the semantic understandings that the LLMs offer? So let's take a look at the solution of the paper. Well, we have what we call a header file decomposer, which is a hybrid phase-based approach to enhance the LLMs. So firstly, we have phase one, which is code parsing and initial grouping. This will ingest that God header file for that first step, and then do the two-stage grouping that we'll talk about later. And then we have phase two, which is a factual knowledge enhanced prompt construction. And then we have phase three, which is hallucination and detection and correction for the LLM, like we were discussing earlier for the hallucinations. And then we have this phase four, which is a cyclic dependency resolution and then automated refactoring execution. But the POA for this phase is to generate a new subheader file that'll be used within the other modules, and then updating the include statements and all the source files that are included in the original header file. And then we have the three core innovations for this paper. One is that stage grouping, phase one, that uses the traditional metrics and LLM semantics. And then we have the dehallucination, which is using fact injection, validation, and correction. And then static analysis integration, which is the ground truth for the LLMs. So looking at some of the key innovations that are offered within this paper, we'll start with stage grouping. So stage grouping solves the context window problem that we discussed earlier, and we do this in two stages. The first stage is the microclustering, which uses traditional similarity metrics, and then we do a macro clustering where the group summaries are provided to the LLM to generate a decomposition plan with reduced hallucinations. And we know this works because one, microclusters are small and easy to summarize, and two, the LLM sees only the summaries which fits into that context window. And this stage grouping approach enables the LLM to process lengthy header files indirectly by operating abstractions instead of raw code that we'll see. Looking at dehallucination, hallucination is an inherent limitation of the LLMs that can't be fully eliminated. So in order to solve this, right, we built a hallucination detection and a correction module to identify and rectify the errors in the LLM generated decompositions. So some of the errors addressed, we have two of the primary ones that we're looking at for this paper. One is irrelevant code entities, and this is where code entities are included in the decomposition, but they do not belong in the original God header file. In this case, we just remove them from the decomposition. And then we have missing code entities, but these happen when certain code entities are from the original God header file are absent from all newly generated subheader files. In this case, we calculate their similarity with within each subheader file and assign it to the missing entity to the subheader file based on the similarity score, which is backed by a code relationship weight between the classes. So looking at this formula, we'll define a missing entity as M and then a subheader file as h of I for a collection of entities E1 to EK. And then firstly, we compute the overall similarity between E of M and each entity E of J within the header file as an average of all 4 relationship weights detonated as an overall sim. So we're really trying to get that average between all of them. Finally, the missing entity E of M is assigned to that new subheader file with that highest similarity score. The reason for dehallucination is because we need those 3 lines of defense. One is fact injection, and then validation and autocorrection. So a key here: do not trust LLMs blindly, but also don't discard them entirely. What we need to do is verify and correct as we go. Looking at some results from the paper, we have 2 research questions that we're going to ask. The first one is, can the header file decomposer address the limitations of LLMs and outperform existing approaches that are out there? And then the second one is going to be, how effective is the 2-stage grouping framework for those lengthy header files that we'll see? So firstly, let's look at the data set that we'll be testing. This table presents the characteristics of each group and the complete data set. For header files with fewer than 200 code entities, I have them colored as blue here. The approach directly provides their complete code content to the LLM for decomposition. So we skip that second step. For files that are containing 200 or more entities that I have colored in red here, we apply the 2-stage grouping framework. First, we cluster and summarize related code entities before presenting the condensed representation to the LLM. And then we can see these total amounts as well that I have colored here in purple that we'll be running the tests on. So looking at the baselines, right? First we have Wang, which is a proposed approach that utilizes code metrics to assess an entity similarity and also uses a multi-view graph clustering algorithm to cluster code entities within header files. And this achieves significant reductions in recompilation times. However, manually designed code similarity metrics cannot accurately capture the functional relationships of code entities. And then we have these 2 models, GPT-40 and then DeepSeek V3, that we'll be using alongside our hybrid approach, which is going to use each of those as well, combined with our approach. So looking at the first research question of overall performance, right? Before we dive into the actual data, I wanted to give you a background of the accuracy acronyms that are here on this data set. So starting with ACC, this is the accuracy, but it's a mapping between the predicted versus the ground truth cluster labels, and they use Kunz-Munkres algorithm as well for this. The F1 score is also a metric for evaluating the clustering performance and combines precision and recall. The Mojo FM stands for move and join effectiveness, and it measures the number of move and join operations required to transform architecture A into architecture B. And then we have the ARI, which is the adjusted RAND index. This is a similarity between 2 data partitionings, and higher values are here indicate that they're better clustering. And then lastly, we have the NMI, which measures mutual information between the predicted and the ground truth clusters. And this is all coupled into one accuracy section on the right hand side of this overall performance. So firstly, we can see GPT and DeepSeek both failed to generate outputs for 1 and 7 header files due to the degraded performance on lengthy inputs, whereas our approach had a 100% completion rate. Next, we can see our approach reduced hallucinations in LLM generated outputs. As you can see, the number of incomplete cases dropped dramatically from 122 to 110, and then 107 to below 5 in our sense. Now we'll look at the cyclic dependencies. The approach enhances LLM's ability to generate decompositions with fewer cyclic dependencies. Even though the LLMs are already producing fewer than Wang's approach in this sense, our enhanced prompts reduce them even more, allowing the LLMs to gain better architectural awareness. And then lastly, we have the accuracy section that we were talking about. we look at the decomposition accuracy. Our approach is still outperforming the base LLMs across all metrics that we defined. So to answer research question 1, the hybrid approach effectively addresses LLM limitations in header file decomposition, and it also leverages their code understanding capabilities. So research question 2, right? The effectiveness of the two-stage grouping framework that we proposed. The initial grouping achieves input reduction while maintaining high accuracy, condensing an average of 343 code entities into 77.5 groups with a whopping total of 98.1 accuracy score here that I have highlighted in this blue box. Next, we can look at the results compared to Wang's traditional approach. Firstly, starting off, DeepSeek v3, like we said earlier, failed to generate outputs for 7 out of 12 of those lengthy header files, where our two-stage grouping allowed us to process all those files with DeepSeek v3 as our LLM. So you can see in the green highlighted area that our method achieved slight improvements in ACC and Mojo FM scores, with a minor decrease in the F1 score section. However, if we compare apples to apples of short versus lengthy header file decomposition, the quality for lengthy header files still remains lower, which means even with our framework, the LLMs continue to face challenges with complex inputs. So diving into the conclusion, this paper introduces the hybrid approach header file decomposer that enhances the LLMs to use stage grouping and dehallucination techniques for effective header file decomposition. By integrating a two-stage framework, knowledge-enhanced prompts, hallucination detection, and correction, our method addresses the limitations of purely LLM-based solutions. So firstly, we'll look at the two-stage grouping, and then we built that knowledge-enhanced prompts that feeds back into the LLM for the hallucination detection and correction, and then offering that cyclic dependency resolution. So comprehensive evaluations on 153 real-world header file decompositions demonstrate that the header file decomposer significantly outperforms state-of-the-art methods, delivering more accurate and more reliable results in the end. Thank you for your time and attention today, and that concludes my presentation.